You open an app on your phone, type a message, and hit send. In less than a second, your screen updates and a notification pops up on your friend's device across the world. It feels entirely frictionless. Beneath that single second of activity, a globally distributed machine coordinates thousands of distinct operations, routing data, verifying identities, saving backups, and updating feeds, all simultaneously. Building an infrastructure capable of executing those operations millions of times a second, without failing, is the core challenge of system design. Imagine a new social platform. On day one, the entire application runs on a single centralized server. With a few dozen users, the requests form a steady, manageable trickle. The server reads the data, writes the posts, and sends the responses with ease. Then a celebrity joins the platform. Traffic spikes from 20 requests a second to 1 million requests a second. The machine's processor maxes out, its memory fills up, and the server collapses under the sheer volume of data. The immediate instinct is to buy a more powerful machine with vastly more RAM, a faster CPU, and larger hard drives. This is called vertical scaling. For a short time, the massive server absorbs the heavy traffic, but user growth is exponential, and physical hardware has a hard ceiling. You eventually reach a point where the largest available server on the market cannot keep up, creating a single point of failure that threatens the entire business. To survive massive growth, engineers abandon the single machine model. They distribute the workload across an army of smaller servers, a strategy known as horizontal scaling. Directing traffic to dozens of individual servers requires a central coordinator. A load balancer sits at the front of the network, acting as a traffic cop that receives the massive incoming stream and divides it evenly across the server fleet. To keep the system maintainable, the application is divided into independent microservices. The code managing user profiles, the newsfeed, and the search function are separated into isolated clusters that can be scaled independently. This separation reaches the storage layer. Relational user accounts, which require strict accuracy, are stored in rigid SQL databases. Meanwhile, the massive flood of social posts is directed to flexible NoSQL databases designed for high-volume scale. This multi-layered architecture solves the capacity problem, but moving data between so many different machines introduces new bottlenecks in retrieval speed. When a user makes a post, the HTTP request hits the load balancer and is routed specifically to the write API server. The write API server then attempts to save that incoming post directly into the database layer. Writing to a physical disk is the primary latency bottleneck in real-time applications. If millions of users wait for a hard drive to confirm a save, the entire system slows to a crawl. Caching solves the problem of read speed. By storing frequently accessed data in temporary memory, the system can bypass the slow database entirely and pull information instantly for the user's feed. Message queues handle the write speed. The system accepts the post immediately and uses a background process to asynchronously fan out notifications to millions of followers without making the original user wait. These caches and queues protect the core database from collapsing, allowing the system to maintain high performance while the underlying hardware scales. In a distributed system, failure is a statistical certainty. Hard drives will degrade, power will fail, and global network cables will be severed. This diagram illustrates the CAP theorem. It defines the three properties engineers must balance: consistency, where every node sees the same data; availability, where every request gets a response; and partition tolerance, where the system survives a network break. In an unpredictable world, partition tolerance is a requirement, not an option. When the network breaks, the laws of information theory force a choice. You can guarantee that the data is perfectly consistent, or you can guarantee the system remains available, but you cannot do both. Because mathematically perfect systems do not exist, the architect must choose which specific flaw is least destructive to the user experience. A social media platform typically chooses availability over consistency. It is better to let a user see a slightly outdated follower count than to crash the entire application while waiting for servers to sync. A banking application makes the opposite choice, prioritizing strict consistency. The system will intentionally freeze and deny a request, rather than risk processing a transaction based on an incorrect account balance. The discipline of system design involves managing the tension between scalability, reliability, and performance. In the real, unpredictable world, the most resilient architectures are those that strictly account for their own inevitable failures.